I know you might think we've been here before, and admittedly, one of our very early tutorials was how to set up a reaction diffusion system in Houdini. However, what we didn't tell you then is that reaction diffusion systems can be set up very differently and can be made to behave very differently depending on their input and simulation parameters. In order to properly set up such a system, we are going to build one from scratch using OpenCL, using what we learned in the past lessons. We will be using OpenCL because it'll just plainly be quicker than using traditional techniques like Vex or VOPs. We will be using OpenCL also to be able to drive the intricacies of our system and to fine-tune and dial it in. So let's get started. After creating a GeoNode, diving in there and deleting the file node, I'll first create a VDB, and I will just create it from a frustum, so I'll set it up to have a size of 7 by 7 by 7 units, and let's set the scale by size, and set the scale to 0.05, so each voxel has a length of 0.04 units. And we would like to create 4 volumes here, and let's call them A, B, temp A, and you guessed it, temp B. Middle mouse button on it, and we see we've got those 4 volumes. However, they have a size of 0, 0, 0, so let's activate them. And now we have 4 active volumes here. Our volumes A and B will store the chemicals that a reaction diffusion system consists of. Chemical A and chemical B, and temp A and temp B will be needed for swapping for the right back kernel in our OpenCL, as we did in the last lesson. So let's initialize B first by creating a sphere, setting it to be a polygon, frequency of 8, and let's dial down the uniform scales to say 0.3. Create a VDB from polygons. Let's hop up here and right click on the div size here, copy parameter, and paste it as a relative reference in the VDB from polygons here to make sure we create a volume of the same size. Let's uncheck distance VDB and enable fog VDB, and let's call this B. Let's also fill the interior and wire this up in here, and we have a tiny fog volume with a sphere here. Next, let's drop down a volume wrangle and use that to just set B as a constant value of 1, like so. And now use these values we generated here to fill our grid A as well. So another volume wrangle, wire our main grid in here, and our initial seed for grid B in here. So what we first want to do is we want to copy these values that we initialized here into the B field. We want to copy it over to that B field that we created here. And I will just do that by going float B equals volume sample, and we want to sample the volume coming in through the second slot, that's the ID 1. Want to sample the primitive with the ID 0, that's the first primitive, coming in through this here, the first and the only primitive, and let's sample it at our current voxel position. Like so. Let's highlight this, that worked, and let's also set A by just subtracting B from 1. So F at A, float value A equals 1 minus B. So it's just the complement of what's stored in this volume here. Let's attach a delete and a volume slice. Let's set the delete to delete primitives, and let's delete everything but volume A. Highlight the volume slice, and we can see here, let's set our volume slice to black body here, and we can see that where the seed is, the values are 0, and everywhere else the values are 1. And in our B volume, it is just the opposite. Where the seed is, we have values of 1, and outside of the seed, we have values of 0. So that's working. Next, in order to bind our volumes to OpenCL, we have to convert them from OpenVDB volumes to standard Houdini volumes, and let's do that with a convert VDB and convert our volumes to a standard Houdini volume, which is indicated by this slightly greenish color as opposed to the bluish color here for our VDBs. Now that we have this, let's drop down an OpenCL wrangle here. And let's first bind this. First parameter should be the volume called A, and that of course is a volume, which is the first volume, so we can't align it, and we want this to be writable. And the volume is called A that we want to bind. Let's bind our second volume, call this one B, again a volume. This can be aligned. It should be writable as well. And let's call it B. Now for the write-back kernel we need temp A and temp B, which both should be a volume as well, and make them writable as well. Again, temp A and temp B. Now that we have this, let's go into the option and let's run over the first writable volume. So we want this to go through volumes. And in the kernel tab, let's generate a kernel first, which is a bit bigger. Let's copy this and check use code snippets so we can write code here. So let's paste our kernel code there. And let's just highlight this to see if it runs. Okay, nothing to worry. Let me just skip to our file from our last tutorial. The kernel that we written last time, which is basically this here, which we used to find edges in the volume, is called a Laplacian. And it turns out that's exactly what we need as part of a calculation for a reaction diffusion system. So it's really handy to just copy this block of code here from our last tutorial, head over to our current file, and after we've done all the initializing and housekeeping, let's just paste this bit here. And we have to adjust it a bit. In our case, our volume that we want to run over is called A and not density. So let's get rid of the density stride offset and turn it into A stride offset. Same goes for these strides for X, Y, and Z direction. And we'd like to sample our A volume here and not the density. Let's check. Okay, that's running smoothly. Instead of calling this variable here sum, let's call it Laplace A, and make sure to change this down here as well. Laplace A, and we need the same thing for a volume called B. So again, let's copy this, and maybe let's add a comment here. Calculate Laplacian of volume A, and again that's kind of an edge detection. Paste this again. Add a comment here. Calculate Laplacian of volume B. Let's call it Laplace B this time. And let's sample our volume B. Okay, that's working. Perfect. Now in theory we are ready to put down the formulas needed for reaction diffusion. And let me just show you where to find them. So when you Google reaction diffusion, you come along this page. It's by Carl Sims. And it's a really neat tutorial on how reaction diffusion works, what its underlying principles are, and how you calculate and simulate it. And you arrive at this slightly scary formula here, but it is really nicely annotated here. So we can actually take this and pretty much enter the exact same formula into OpenCL and end up with a reaction diffusion system. So let's do this. And this will be here. Again, comment it. Reaction diffusion equations. And first we need to store our current values for A and B. So let's call this old A, and it will be the contents of our current voxel. And do the same thing for B. Let's call it old B. Current voxel position in B. Now let's calculate the new values. Let's call them new A. And it will be equal to old A plus, and let's put down parentheses here. And before we actually start writing down our equations, what I want to do is comment this out for a second and set up some additional variables that we will need in order to drive the behavior of a simulation. It's going to be a variable called dA, which will scale the Laplacian of A. Let's set this to 0.1. We will do the same thing as a scaling factor for a Laplacian of B. And let's set this to 0.02. We will need a float storing our feed rate. Let's call it F. And it will be 0.1. Our kill rate, let's call it K, will be 0.085. Finally, our time step, let's call it dt, will be 1.0. I will go over what these do in a second. Let's now uncomment this here and start writing our formulas. So our old value plus dA, again that's just a scaling factor, times the Laplacian of A minus old A times old B squared. And let's just write that down as old b times old b plus f times parentheses 1 minus old a times dt. Quite a beast, but when you look at it, it's extremely similar to what's written on Carl Sims's page. Let's drop down the equation for our new b. And this will be our old value of b plus parentheses. And it just occurred to me that these parentheses are wrong. Should be like this. Back to our new b. Our new b is our old value of b plus our scaling factor for the Laplacian times the Laplacian of b minus old a times old b squared. And of course, this should not be a minus, but a plus. I'm just jumping back and forth between Carl Sims's page and this editor here, so excuse the typo here and there. Minus k plus f, and let's put that into parentheses, times old b times dt. And let's write out those values into our temp volumes. So temp A equals temp A idx, of course, equals our new A value, and our temp B equals our new B value, like so. Now finally we have to create a write-back kernel and write back those temporary volumes into our main volumes. So let's check use write-back kernel here, and we immediately get an error message which we're just going to ignore for now. And for the write-back kernel, let's just copy all of this here, scroll down the end of our code, and down here, let's drop down our write-back kernel. Let's call it write-back, same name that's given down here. And up here, let's just set our A volumes voxel value to our temporary A volumes voxel value, and do the same thing for our B volume. Fingers crossed, and that is looking promising. Okay, after we've done that, let's delete everything but our B volume. Delete non-selected, and let's highlight this, and we can see we have our standard seed volume here. Not much changed. However, what I can do now in the OpenCL SOP, under the Options tab, I can increase the iterations to say 128. And I can see there's something happening there. And we can drop down a convert volume SOP here, via the SOP, and convert this into a polygon. Let's just increase the ISO value, say to 0.5. We can see there's something happening there. And when we still increase the iterations here, say to 512, and of course this takes a while because the whole node has to run over the volumes 512 times, you see there's something developing here, there's something evolving. So let's set this back to something small like 32. You can regard this as our sub-steps here, because what we're going to do is we will drop the whole thing into a solver, which we're just going to wire up in between here, and then just cut, go into the solver, and paste our OpenCL wrangle down here, and highlight it. Let us go up one level again, let's save this, and hit play. And you can see now we have the system evolving over time, and the simulation spreading over time. So this is our very basic reaction diffusion system in OpenCL.